What is a space elevator? How does that work? Next chart. We just did this report about 2 or 3 years ago. The International Academy of Astronautics, 1,000 guys elected who are experts in space. We all got together. But what you need to know is a bunch of smart guys got together and came up with the answer that space elevators are feasible. Now, the secret here is most of those 1,000 people are rocket guys, rocket ladies and men that have been working on the whole lives with rockets, and they're saying, well, this might work. Next chart. So we're going to talk about these different items today in my section, but we're going to talk about why. And I talked a little bit about it before. Next. We can change the world, how we approach outer space, interplanetary travel, construction, repair. Those would be routine if the cost to orbit is only $100 a kilogram. Next. This is my vision. This isn't ISEC, this is my vision. We're going to have access to the solar system so inexpensive and so routine. At L1, we can have a colony, mining of asteroids, pulling off the water and the fuel, putting it on our interstellar ship. We can do that at L1 if it's only $100 a kilogram to get off the Earth. Next. And why is that so important? Look at these stupid numbers. God, I hate these numbers. Robert Heinlein said, if you get to low Earth orbit, you're halfway to anywhere. That's true. It takes us a huge amount of energy to just get up into low Earth orbit. From there, it's almost nothing. Except that, to get from low Earth orbit to where you want to go, you got to use fuel. And where does the fuel come from? Oh, bummer, man, it comes from down there. So you got to lift the fuel off first, and then you can go someplace. So it's a double problem. So if we can get fuel from asteroids and the moon and stuff like that, it'll make it a lot easier. But our problem is this first 9.3 kilometers per second velocity required to get up to low Earth orbit. Next chart. So that's what we want to do. We want to have a reason to go do space elevators, and the answer is we can really brighten up the human spirit. Next. So if you think about transcontinental railroads, whichever continent you're from, they built a railroad across there. In the U.S., it was in 1865. Before the transcontinental railroad, it took roughly 6 months. It cost about $1,000, and you had a reasonable probability of dying. Okay, you went around the Horn. That wasn't very good, bad weather down there. You went across the Isthmus of Panama, a lot of typhoid and malaria and stuff like that. That wasn't good. Or you could walk across the country. And that took 6 months, and there were Indians shooting at you. So, or you get stampede of buffaloes or something. I mean, it was dangerous. In 1865 or 69, they put a train across there, and you're going 90 kilometers an hour, man. That was something. Got across the country in 6 or 7 days for $70. Amazing. Next, and that's what we're looking for, changing the paradigm. Okay, history, next. We just did this book. I think it's right here. Where'd it go?
I don't know.
Oh, right here. It looked, well, we don't have it. I guess somebody borrowed it. But anyway, it looks like this. And we did the history of space elevators. And that's kind of funny, right? We haven't ever done one. But we decided to record the approach to get there. So we started in 1895. It's been around since 1895. So we've been doing a lot of stuff. And then there's the science fiction. Holy Toledo, everybody loves the idea of space elevators. The only problem is the theme is to cut it and have a dangerous situation. We don't like that. Okay, next. Some more. Next one. Okay, so system introduction. What is a space elevator? Roughly 100,000 kilometers straight up from the surface of the ocean, basically 1,000 kilometers to the west of the Galapagos. We just go straight up. And how do we stay up there? Well, the answer is like a rock and a string you toss around your head. Centrifugal force, the ball stays out there. So what we're going to do is we're going to put a mass out at 100,000 kilometers going at the speed to stay relative to the point on the Earth. So therefore, it's the same thing as a rock around like that. And if you toss it that way, centrifugal force puts tension on your tether, so you have a stiff tether. course, down at the bottom, you got to grab it. I always think you got to grab it with something like an old aircraft carrier. You got to have a lot of mass down there, you know. So that's the way it works. In a geosynchronous, where everybody loves to be for money, you know, like commercial geosatellites, weather satellites, stuff like that, that's going to be a big active place. And then you have tethered climbers going up, and then you have the end mass up there at the top we call the apex anchor. Now the real answer, if we're going to transform transportation in the solar system, is as you go up that tether, your horizontal velocity increases. It's a linear thing. You go up, horizontal velocity increases. You get to geosynchronous, well, you start at the equator, you're going 0.5 kilometer per second. When I was swimming with the sharks in Galapagos, by the way, there's a lot of sharks in Galapagos. When I was swimming with those guys, we were going 0.5 kilometer a second. They're really fast. Okay, then you go up to geo and you're going 3 kilometers a second, and you let loose and you just sit there because that's the synchronous point. You go up higher and higher, you get to a certain point, you can release and go to the moon, no chemistry required. Go up higher, you get release and go to Mars, no chemistry required. Of course, you have little rockets do corrections, and then when you get there, you got to slow down, so you got to have some rockets here. But you don't need the big chemical thrust to leave our Earth system to go to the other parts of the solar system. Okay, next. So here's a little look at that, and we've started giving them names. That's the fun part, naming these things. See, we're at the forefront of the whole thing, so we get to create names. I love apex anchor. Isn't that a good one? Do we want to vote on that? No, we don't want to vote on that. I came up with apex anchor, but anyway. And we've got the gates are where you let loose. And then we have the centers. The centers are where the gravity is equivalent to. Mars gravity is, you know, a little ways off the Earth. Lunar gravity is a little bit further. So if you have a science center there, you can actually do science on that point. Okay, next chart. That's just for a perspective. We're outside the stinking bow shock. Okay, go ahead. That's the way we deploy it. We start with a regular old rocket to get to geosynchronous. You extend the cable down. You have a compensation mass above that. You let it go up. And so the center of mass stays where it's supposed to. Grab it at the bottom, and then you've got a space elevator. Next. That's what a ribbon looks like. What we want to do is make a ribbon that small debris can just blow right through and won't affect the strength of the whole ribbon. Next. And that's what the details are, and then Mark Haas is going to talk about that at 4 o'clock, and spend an hour on carbon nanotubes and stuff. Next. That's what a Earth port looks like. Your tether's coming down. We've got 2 in that picture. Next.
That's because there are 2.
Yeah, because, yeah, we
This
can
is
see
actually the terminus, not the port.
The terminus, right, at the bottom. Earth port. Okay, then we have tethered climbers, and the one on the left is the one that reels out the tether. You can see the big reel of tether at the top, or in the middle. The fuel tanks are on the top. It takes a lot of fuel to get it up there. Then tethered climber on the right. Next. Okay, our idea in the International Academy of Astronautics' Blue Book here is to use solar powers. Brad Edwards' idea in 2002 is to use lasers. They're both valid ideas. Who knows what's going to end up in the future when somebody says, I've got $5 billion to build it. You're going to say, uh-oh, which one are we going to pick? Next. Ops Center, everybody's seen one of those. Next. Architectures, 3 architectures that are valid today. Next one. Brad Edwards came out with a study. What he did was a NIAC, NASA Innovative Center, phase 1 and phase 2, and then wrote a popular book, not a NASA, well, he did the NASA reports, of course, but then a popular book and sold it on the web. And the book covered the space elevator concept, and his is very similar to what we baselined ours, but he's got 2 things that are different. One is he's doing lasers from the ground to power the space elevator climbers. And the second is he believed we needed 150 gigapascals, so really, really strong cables. Next. You can see the theory here is laser power coming up from the ground. It hits a receiver. You take that receiver energy, convert it to electricity, wheels, motor, turn wheels go up. Next. And his idea of the earthport is pretty consistent with what everybody else has come up with, which is an oil platform, put it out in the middle of the ocean. Next. Okay, then the IAA, 10 years later, with a whole bunch of people studying Brad Edwards' design, came up with another architecture. Next. This is a book outline, but just shows the different parts. We did a lot of research on all the problems that you can think of. Next. The idea in this one was we were using solar power, not lasers. Now, when you decide to use solar powers, you've got to get through the atmosphere because the solar rays just wouldn't make it through winds and storms and rain and all that stuff. So what we do is we box it up. We fold it up like the lower right there, put a box around it. Then we use a box through the atmosphere, the first 40 kilometers. Then we climb out of the box, deploy the solar rays, and then go. That's different than Brad's idea. Next. So it looks something like this, but the tethered climber has a lot of solar cells. Next. Characteristics. I kind of just covered some of them, but we're talking routine every day. 3 tethered climbers lifting off every day. A huge amount of capability. Next. There's our little box for the atmosphere. Next. So now the surprise, when we were about to present the International Academy of Astronautics answers at the big yearly space show, the company, now Obayashi is the company that builds skyscrapers in Tokyo. They're not associated with the government space business. They decided to study space elevators. I haven't figured out why yet, but anyway. And they published multiple stories on that, multiple papers on space elevators. So their concept's a little different. Next. Here's a little presentation they did. Next. They've got 100 metric ton tether climber. We were going for 20 metric ton. The reason they're going to 100 is they want people. They want to have people in their first space elevator. So 100 metric tons, 150 gigapascal, which is really strong material, and they've got 2 tethers next to each other to have redundancy and safety. Next. There's a pretty picture of a 100 metric ton thing going real fast. Next. That's their earthport. Next. Something like that. Next. Yeah, there we go. That's their earthport. So where are we? We're in St. Louis, right. Okay, next. We're in St. Louis, and we've got a schedule that looks something like this. You don't have to read all the details. Big people who have done a lot of space programs did that. The answer is 2036. We hope to be operational. 2036, that's just around the corner. Next. And this is the Obayashi schedule for humans, and they're looking at 2050. So theirs is pretty much on track with ours. Add 15 years to do the human part versus the robotic side. And then we have joined us, ISEC, this is a straight advertisement, International Space Elevator Consortium. We have a little thing, newsletter, check out our website, that type of stuff. Next. Okay, any questions before we transition over to Fisher? Yes.
When you let go, if you're going to go to Mars or something like that, you got 23 and a half degrees that you got to account for because it's not lined up with the plane of the ecliptic, if I'm visualizing that right.
Yes. What you do is the big velocity straight at the planet location where it'll be in, 5 or 7 months is the big velocity, and that's your toss. Then you have to have chemistry to change the plane, right? And the equation is something like cosine of the angle times the velocity. So you would want to do that right, when you get going, and then change the plane. Yeah, it's in there. You can look at that. Okay, 2 more questions, and then we'll.
Did I read correctly that the entire cable would be 20 tons?
No. The initial cable mass would be about 40 metric tons for the first cable would be a very small string, not capable of doing anything. That's the single string we put down. That'd be light. When we get to the full capability, it's like, what did we agree, 1900 metric tons would be the tether, something like that. Then one question over there. Okay, the equator is very nice because it comes straight down. If you go off the equator, it's a cosine factor loss of payload capability. So you don't, a few degrees, nobody's going to care. Location on the equator, we don't want to be in a country that's not really robust, where they could nationalize it or something like that. So we want to stay away from countries. Open ocean international law is very conducive to having a major asset that you can protect out in the middle of the ocean. So it's a very likely place.
And that's why you hire an architect to go find one.
Right, and we actually hired an architect to go find one. He was a student at the university in Helsinki, and he did a really good job. He's talking about another guy. Okay, we'll have more questions in a few minutes. We've got to run through this in an hour. Okay.
Okay, I'm Fitzer. I am, at Pete's request, the chief architect. Pete called me in 2012 or so and said, Fitzer, we have scientists and it's like herding cats. I need somebody to bring a little system engineering and architecture engineering. And if you go and look back at architecture engineering, which is a step above system engineering, and that's a whole nother meeting, is one of the first things you really need to do is to agree to a common vision so y'all are working the same problem. Okay, so the next 20 charts is the factual story of how we came to what we now call the vision. Next chart. Now the vision, therefore, and then, is the basis of our strategy. So we've inverted that logic in our case. We are going to build a transportation system with the knowledge that it will induce an enterprise of entrepreneurial activity in space. How does that work? And that's what the vision need is all about. And we are going to do, as we say here, build a galactic harbor, and let me explain what I mean, or what we mean by a galactic harbor. Now remember, this gives us a common vision of what the space elevator should look like. It doesn't define the design. All right? It's an attitude and an approach, okay? Okay, go ahead. This chart is meant to represent, quote, everything that Pete just said. Okay? Next chart. We asked somebody who was the chief engineer for the Port of Los Angeles and knew a great deal about marine engineering, what does an earth port look like, since it's likely to be in the middle of the ocean? We got to ask somebody who knows about water. And this is basically what his story is that if you look up there, and I don't have a pointer, I apologize, the FOP in the middle is a floating operating platform or an island, as the Japanese like it, and we'll have two tethered terminuses, probably 20 clicks in either direction on the surface of the water. Now he's the one, Vern is his name. Vern is the first one that indicated that 10, 15 kilometer separation is sensible for his purposes. There are other reasons for separation for other purposes. And I write these purposes down because they will eventually become system engineering, architecture engineering criteria. Next chart. We're going to put it, and it looks like, in spite of what Pete just said, the Central Pacific is looking better for a number of reasons, which I'll be glad to talk about. All right, that's a whole nother report. Next. This Earthport is serviced by police little boats and little boats that do surveillance and repair, and next chart, and handle the payloads when they come from the space providers. All of this is going on out in the Central Pacific somewhere, and in our current opinion is a few hundred miles south of Howland Island, which is where Amelia Earhart got lost, or someplace like it. Next chart. That's the Earthport, and these are the two tether connections, and that's a chart that Pete showed. Now those two tethers each connect to what we call the apex anchor. This is our current vision of it. Next. And there are two of them as shown there, okay? And this is our current vision of what the apex will look like at IOC. The big ugly green thing in the middle with the green legs on it are indicating that there's pretty clear evidence from a physics standpoint and Kepler that we need to have a structure up there that holds the you-know-what together. In addition, I put little gadgets in there. We need to monitor this from a surveillance and closed-circuit television basis inside out constantly for all sorts of reasons, all right? That's our vision of the apex region. Next chart. The chart I just showed you is the transportation system. This is the Enterprise system because the Enterprise will be doing interplanetary stuff. And before I confuse you, those interplanetary missions will be coming and going from here and from two other locations I'll show you in a moment. Next chart. Originally, we thought this is what the GeoNode would look like. Very simplistic, just place to drop off satellites as you go by. Next chart. We thought about it for a while and said, well, if you're going to put several tons of tethers and whatnot up there, maybe we ought to have a place to park gadgets that help the test and deployment process. So we put a parking lot there for IOC on the upper right. And then there's my green orbits of sensors so I know what's going on. That's our initial operational capability vision of what goes on at geostationary. Next chart. Next chart. Because if I'm going to service things, okay, those things that are stationed at geo or arriving at geo, I'm going to have a service orbit. If I'm going to keep things at geo, I'm going to have parking orbits, and I'm going to have surveillance satellites that are looking at all of that so they don't bump into each other. And by God, that's magic. We know how to do it, but we don't know how to do it for a whole lot of things. And we're seeing in our vision that geo has a whole lot of things. And by the way, I should report that all of what I'm saying here is in a report that Pete and I and 6 other people are going to put out in
2 months.
2 months. Next chart. In addition to all that, we have, and these are ads, we can have very specialized satellites, that's in the lower left, and that's a whole 6 chapters in another book yet. And in the central region, the GeoNode operating platform will generate power, data processing, security information, la-di-da-la, all of that will be going on in the red string in the middle. Okay, that's our vision of the functional aspects of the space elevator. Next chart. Whew. But right there is clearly a discussion of a traffic jam. All of that going on, how do I organize it? And here's how I came up with the notion of a harbor. Next chart. This is literally a picture at the end of my street, up a block, okay? You see that? But if you zoom in, that's what I see every day when I go to work. And when I started going to work from this house in 1974, none of that was there. Okay? That is a picture of the 2nd largest container harbor in the world. Next chart. Sometimes it's pretty. Next chart. There's an aerial view. This is amazing to me. 1 million jobs in California. Technically speaking, in the southwest United States, almost all of them in California. 15 million containers per year. A container is what fits on the back of a truck. The thing is about 12 to 15,000 acres, and that's the land part of it, not the water part of it. And each year we send through 500 billion. This is a busy place. It's an incredible complex. And frankly, I lay in my bed on some Sunday mornings when the wind is just right and it makes a racket. But it's $500 billion worth of racket. Next chart. So Pete calls me, said, Fitzer, I'm building a space elevator. And I said, what the hell's a space elevator? And amazingly, next chart, this is what he explained to me. He didn't give me that string and then he said, Fitzer, it's a place that goes from the Earth port up to the apex, and it's going to have 3 or 4 stops. Mars Gate, I said, Lunar Gate. Next chart. So I wandered around for a few days and took this picture and sent it to him. Now I'll tell you a secret, Pete didn't understand it. Because this is what I was trying to explain to him. Next chart, which is a blow-up of this. So I'll shout for the next moment or two. This is Fort MacArthur. It's part of the Los Angeles Air Force Base, where they build basically satellites for the Air Force and other activities, okay? That's part of it. This is a container ship from here to here, and there's the back side of one, and there's another one, and there's those cranes I showed you. There are 6,000 containers on each of those ships. 6,000 easy place. All right, you see these palm trees? That's the Coast Guard station. They've been pictured a day or an hour or two earlier than a couple of Coast Guard cutters. This is the prison. Turtle Island Federal Prison. There's some bad guys here. To the left of the prison, for about 2 miles, was dozens of repair shops. Dozens of them. Okay? Now looking over here, the bridge from Wilmington, California, into Long Beach. You getting a picture of what's going on here? And then, of course, there's the tourists and the rich guys with all those boats parked in the yacht harbor. That's the Caprio Yacht Basin. So my thinking was that this is what we're building, but in space terms. Next chart. So you take what I just said, and there's you can get this from Google Maps. Let's click. Okay, for perspective, I live right over here, just off. Right? And there's the one bridge. There's another bridge. There's Howard Hughes Spruce Goose Parking. There's Long Beach Queen Mary. This is where they have a Long Beach Grand Prix. And the rest of this outfit, as I was saying, does $500 million a year. Next chart. Oh, you went too fast. Back one. Back one.
Back one.
Push it. Push it.
Who's got control? That's interesting.
This is the crowning moment of the connection between a harbor and people.
Okay, let's try it now. There.
Now, so I took that Google map picture, and I saw all of these piers and wharves and ports of entry and cruise ships and tourists and love boats and prisons and all of that stuff. That's what's in the harbor. So I just drew some red lines about it. And I said, I'm going to correlate those red lines to Pete's places, which I put red lines about. Those are the wharves and the points of departure for the space elevator. Back one. If you're going to have to go back, there you go. The thing that makes this work together is the main channels. Okay? The main channels. Go forward one. One more. So our main channel is the tether and the climber and connects these places. So the totality of the harbor goes from the earth port to the apex anchor, and all of those are wharves and quays. Now the reason I do this, and the reason it's in a sense required by the architectural engineer, is we're going to do functional allocations and delineation so people aren't getting in trouble with it. We're going to build this thing. You got to go through this nerdy stuff to figure out what you're going to build. And that's what we've done. Next. Showed you that one. Next. That goes down here at the bottom. Next. Next. What we're saying is you take all of that harbor thing and you build this. but we have a longer-term vision for the same harbor. Next, this is what we see coming. Next, a bigger space elevator, and then even beyond that, a research space elevator. Now, they may all be in the same place. I don't want to do that, but they're different. And that is our vision. All right, I'll take questions.
Well,
a couple for clarity.
We're going to take questions in a few minutes. Let's go first
Yeah.
to Brian.
Okay, if there's anybody that doesn't get anything, I'll be in the back. And where's Brian? I don't see him.
Right there.
There you are.
Okay.
I'm sorry about it. We're doing good, though.
Yeah. Well, I'll probably yield back some time here. Mine's pretty quick. I'm Brian Long. I'm a naval facilities engineer. Been with the Navy for about 14 years. I'm currently working on a master's degree from the Naval Postgraduate School in systems engineering. So the topic of my thesis, which I got to preface this, I'm not as far along in my thesis as I would have liked to be. So a lot of this is what I'm going to be planning to do with Dr. Swan as one of my advisors here. So just real quick agenda, I'm going to talk about a reason why I'd want to study this, systems engineering. We heard a little bit about architectural engineering from Fitzer, and then going to state my hypothesis, and then the first test case that I'm going to look at. Next slide, please. So if any of you have young daughters, I've got a 4-year-old. She loves the movie Moana. If you haven't seen it, it's actually a pretty cool movie. But it's kind of cool in that, they're trapped on this island, they're running out of resources, and this little princess has to go out exploring. It's a pretty big corollary to what this whole, and I'm new to the space industry, by the way. Like I said, I'm a facilities guy, so I think it's kind of a cool corollary to what everybody's trying to do here. In terms of the Navy, any expedition you're going to do, the more complex it is, you need a good transportation system, and you need a supply and logistics chain. Next slide, please. So with respect to the Navy, and how does the Navy and the Department of Defense fit into the space arena? We do a lot of cool stuff, actually. We do a lot of cool expeditionary stuff all around the world. We've got a lot of systems. We get, and I'm sure a lot of you know, we get a lot of money to do a lot of this stuff. Probably, some of that money, what I would like to see could be dual purposed for some of the systems that we're talking about within the space environment. Next slide, please. This is just for those of you that know about systems engineering. This is the dreaded V model, which is basically saying any system has got to go through this hoops to actually validate the system and make sure it's something that can be proved out. I show there the 14 steps essentially through the international consortium of systems engineers. Where I'm going to be focused on with my thesis is just basically who defining the stakeholders, and then from where I'm sitting, it would be the Department of Defense, and then what are those requirements and trying to define those requirements. Next slide, please. So, like I said, turning needs into requirements. How does that? And it's kind of a two-way street. So what would from my perspective, what would the Navy, Department of Defense benefit from? And then obviously what could we contribute if we were a major stakeholder in the space elevator system? The second bullet there shows a number of ways that we could contribute. I'm not going to go into each one of them, but next slide, please. So this is my hypothesis. It's basically what I'm going to test out over the next 3 to 4 months. I'm supposed to graduate in September, so hopefully I'll be done by then. We'll see. Is basically I do believe that it is within the Department of Defense's best interest to try and at least support this concept in a number of different ways. A lot of it right now is obviously on the R&D, the conceptual phase, but there's obviously a number of good reasons. The low cost, reduced schedule, reduced risk. I'm not going to focus on which actually, as I was watching the other people's presentation, there's a whole aspect of the the port. So if it's in the middle of the Pacific, obviously the Navy would be interested in that. But I'm not going to talk about that. Next slide, please. So this is going to be my first test case, which is basically saying, okay, there's a lot of money spent on satellite, DoD military satellite communication systems. So that'll be my first test case, and those are some of the questions that I'm essentially going to be going to start with asking and then trying to answer within my thesis. And I think that's it. I plan on, obviously, like I said, hopefully graduating in September and, publishing this through Naval Postgraduate School and then possibly through the Space Elevator Consortium. Thank you.
Okay, thank you. You put that over there. Okay, so that was the first hour. We'll answer some questions now. So all those questions you had for Fitzer, now's the time. Don't ask me any, of course, but you had your hand up first.
Yeah, what's the status of carbon nanotube development now? I haven't followed it.
Okay,
for years, but
yeah.
Let me know where you think it might be usable in.
Yes,
10 years?
I told you that I thought we'd be having a space elevator by 36, so we'd have to be for then. We have Dennis Wright coming up to talk about research, and we'll talk about some of that. But Mark Haas follows him, and he's at the University of Cincinnati doing research on carbon nanotubes.
Can I ask my other question?
Sure.
You have 3 launches a day, you said, right?
One per tether.
One per tether. Are they coming up and down the same one, or can they switch over and go down in a circle?
The idea is you have 3 tethers, so you could have multiple ones going up and one down or something like that. And the idea is you get to geosynchronous and just float over to the other guy. We do geosynchronous movement all the time on all our satellites. And so we understand that. So you just get up there, release, float over to the other one, come down if you want to come down, or go up the other one, or whatever the planning is. Yes?
What is the longitude of the first one?
722 and 2/10. I have no idea.
I have no idea.
No.
I'm just I'm gonna get back and look at my globe and see where it is.
The estimate is 1,000 kilometers west of Galapagos, out in the area. And the reason is, I didn't go into this before, but the reason is that area of the Pacific is Pacific. No recorded rogue waves, no lightning, no storms, no hurricanes. It's right on the equator, so the winds don't develop there and all that kind of stuff. There's no land there, so there's no buildup of rainfall and stuff like that.
I want to go back and look at it.
Yeah, and now if you really want to get into it, there's a master's degree by a kid from Helsinki, and it's really delightful, and it really goes into some neat stuff. Okay, yes?
Do you envision this mainly for cargo or also eventually for human travel?
I believe the way I structured it is robotic through about 35 to 50, and then human from 50 and beyond. So I believe that we'll get to human transport, but it won't be immediately. I think there's enough phenomenons and difficulties and everything else to do it robotically first.
So you haven't really looked at getting through the Van Allen belt and other issues that if you send humans up through these various areas, you have to face in terms of human safety and health?
Okay, we will have to, but it turns out the Japanese have. The Japanese Space Elevator Association and the Obayashi Corporation have a study that says they want to take 100 metric ton tethered climbers that go up with people, and 25 people in each one. And they have looked at the radiation issues, and they have done that. I have not personally been involved, but we work with those guys. So the people version of the space elevator will address all those radiation issues. Now, just to be complete, as an engineer who builds satellites, we have to worry about that stuff too. So all the equipment on a space elevator climber has got to be radiation tolerant, because it's going to spend a week going to geo, and much of that in the Van Allen belts. So our equipment on our tether climbers have to be radiation tolerant.
Do you have a system already designed or in mind for ongoing repairs? I'm assuming there are going to be micrometeorite strikes. They're going to punch little holes that, as long as they get fixed fairly promptly, won't cause failure. If that's going to go unfixed for decades, they'll probably start weakening the strands unacceptably.
Yeah, there have been a few papers. We have a yearly conference at ISEC, International Space Elevator Consortium. We have a yearly conference in August at the Seattle Museum of Flight, 3 days, and we talk about all kinds of topics. And there have been one or two papers on repair climbers. So, go up and you have an optical system looking for holes, then you slow down and you fix it, and then you keep going. So there have been 3 or 4 papers on that topic, yes. Okay, a question back there?
Well, I'd say how secure would this cable be from either accidental or deliberate, hit by an aircraft? I mean, basically, the cable would be invisible, how can you control aircraft accidentally hitting it sometime or another? And would it really damage the cable in that?
It turns out that we'll do the same thing in this arena that we do for anything in America, like military bases or hospitals or stuff where you don't want to have airplanes flying over. You have this big notice that goes out to every airplane in the world that says, don't fly over here. And so that's the first protection. The second protection will have literally military protection, not necessarily U.S. or Japanese or anybody, but somebody militaristic as protection against any terrorism or stuff like that. They'll have to be watching under the ocean. They'll have to be watching for a radius around it. They'll have to be watching for airplanes and all that kind of stuff. So we'll be watching for that. But the bottom line is that material is really, really strong. And if you took an airplane wing at 600 miles an hour, the wing would come off. It would probably disturb the motion of the tether, but I don't believe it would sever it. I think the wing of the airplane would come off. So you don't want the airplanes flying into them, because of the safety issue. So we'll have notices, don't go over there. Keep out zones, stuff like that. Yeah, you had a question?
Well, I was wondering if I'm sure you have figured out, like, where you want to put this in the Pacific Ocean, make sure it isn't too deep that you can't get to the bottom of the ocean. The harbor part.
Well, I believe we don't care about the bottom. What we want to do is we want to put it out there, and we want to move the bottom of the tether so that we can instigate the motion of the tether as a wire as it goes up with the dynamics, because what we want to do is move it out of the way of big stuff. There's a book out there on the on the space elevator table. I have this one. Space elevator survivability and space debris. And it's a manageable problem we've looked at real hard. The first thing is we'll accept hits, so the small stuff, and the numbers are pretty simple. And then we'll move the thing for the big things. Let me just read, where do I have that? Okay, it says here, the LEO region, okay, we define the LEO region 200 kilometers to 2,000 altitude, so basically where LEO satellites are. Untracked, small, less than 10 centimeters, will impact a space elevator in that region, so it's 1,800 kilometers, on the average once every 10 days. That's 1,800 kilometers once every 10 days. Okay, track debris, so greater than that, in that region once every 100 days. So the big things once every 100 days. And track debris will only impact a single 60-kilometer stretch of any part in there once every 18 years. So it's not a huge problem. We would move it for the big things and accept the small hits.
So it's basically not going to be connected to the ground.
Oh, it's connected to a floating platform.
Yes.
Move around.
Gotcha.
And it'll dampen the motion if we have too much motion, or instigate motion to move it out of the way of the big things, and that type of stuff. Yeah. Yes?
Can it recover from being severed at the base anyway?
There's a Professor Paul Williams from Melbourne. I don't remember which university, but Melbourne. He sent in a paper while we were doing that blue book of 180 pages and 5,000 pictures, images and figures of the severs. And he had taken the space elevator and severed it at all kinds of locations. And so if you ever want to know anything about that, I can send you the paper. But anyway, the bottom line is there's probably not much chance of cutting except in the high density areas in debris. So we asked him to cut it at 800 kilometer altitude. So then he did the study showing what happens to the 800 kilometers below. Okay, basically it falls down to the east, and so it falls down. But everything above there would start to go up because the mass is kind of pulling it up. So I came with the conclusion that I believe, as an engineer who's built satellites, that we could instill an immediate response type thing. I mean, we're going to recognize a sever because the tension's going to go away. So you're going to recognize a sever, and then you release tether from the geonode. Now, it's certainly not going to be pretty. That bottom portion is going to go all over the place. But I think you would save the total space elevator. And if you had a few tether climbers above the cut, that would dampen it out even more. So I believe that it's not catastrophe if it's cut at the low levels, which is where the high threat is. But if you had an asteroid come in from out of nowhere and hit it halfway to geo, I think we'd have, it'd be a bridge falling down like a big bridge falling down. It wouldn't be nice. But, builders don't build them to break. We try to make them so they'll work. Yes?
What are the strength requirements of the different three ideas that were presented, different plans? Brad Edwards and the board, and then the Japanese, and what are the...
Brad Edwards did the study, and his answer came out 150 gigapascals for the strength. I really don't know what a gigapascal is, but, I use the number. Mark can tell you all this stuff. But we, in our study, took an earlier study by Ben Shalif, and he said that there's a trade in strength and mass and payload movement. And he did a big matrix on it, and he called it the Space Elevator Feasibility Condition. And he came out with numbers that was like 30 to 35 gigapascals. So he was significantly below Brad. And Brad didn't really, I shouldn't speak for him. The community at the time did not support the numbers from Ben. When we did the study on the International Academy of Astronautics, we had 40 really good space people. And we said, that's really good. So we recalculated it and came up with like 40, 42 gigapascals. The Obayashi guys just published the same time we did in 2014. Remember, they had a different criteria. Humans, 100 metric tons instead of 20 metric ton carrier, and we were robotic. So they had a different set of requirements. And they went back up to the 150 gigapascals. So, it's a what do you want to achieve? What are your requirements for the system? That type of trade. And quite frankly, we got good ideas. We got stuff down on paper. But if somebody walked in and says, here's $5 billion to start the project, first thing I'd do is look at that criteria. What's the real demand on the material? Yes?
I heard anything about dealing with the potential static electric charge built up along the tether, or is that not a problem?
Okay, I would prefer not to ask that. You're going to have Dennis Wright coming up just right now, right? And he's the director of studies, and he's also at the Stanford Linear Accelerator and is an expert on the magnetic fields and the interactions up there. And so ask him that question after he finishes, and maybe he'll have an answer for it. One more? Yeah.
Questions on the motion of the tether. If you see something big coming and you move the base, how long does it take until the tether, say 2,000 kilometers up, has moved? How fast can you move it out of the way?
I don't know the answer, but I've always got these buts. Dennis is leading a study this year, and the study is design characteristics of the space elevator simulation and modeling needs. So we're looking this year, what do we need in the way of simulations and models to represent a real space elevator? So we can answer exactly that question. I've got questions like, how much actual motion will you have at the apex anchor? And if it's just a cable wavering, or if you have a massive end like we pretend, what's the motion? We don't know those answers yet. And Dennis is going to show us the type of simulation and modeling we need to do that.
Well, this could be the second part of my question. Every time I drive to the airport in Seattle, I drive over the successor of the interim scalloping Gertie Bridge.
That broke, yeah.
And whether harmonic vibrations have been looked at either from deliberate movement or an involuntary movement in a storm or a meteorite strike or something else.
Yeah, those are all inputs to his study. And we've given him the inputs, but he hasn't come out with an answer. Our process at the International Space Elevator Consortium is we pick a topic. We don't have that many volunteers, so we can't have too many people. But we pick a topic in August when we have our board of directors in the conference. We announce the topic for the next year. And so the topic includes papers for our magazine and journal, the conference topic for next year, and we do a study on the topic. So then we have a year to do that study. So he got kicked off on August last year, and he's responsible for having most of the answer by August of this year. Now, no need to have it all done by August, but then he writes between August and January, and we have a report in January to March or something like that. And that's our schedule for these studies. So he's more than halfway through the study process on that particular issue. And I believe it's going to be a really good report. When we get it out, there are going to be a lot of questions that I've had over the years that hopefully be at least directional on how to get the answers to so many of them. Let's see, what time is it here? Oh, we got one more question. Yeah, and then Dennis is up.
Do you have any political outreach? In other words, a way to get money?
I have failed miserably. I've been trying to get a pot of money from, say, $500,000 to $3 million to initiate our research. And Dennis is going to talk about our research efforts. And so you can see that they're relatively small at this point. And of course, the $3 million would build on. And I even went to Dubai on a boondoggle and got to talk to the Space Center guys there and everything else, but no money flowed. So I have no idea. I failed miserably. I'm looking for people who could volunteer to help and try to figure out how to fund this.